all of us have kind of, I think all of us have kind of experienced that. So good luck.
All right. Can everyone see the slides here?
Yes, yes, very nice.
Very good. All right. Well, welcome everyone. On behalf of ARMA and the Induced Seismicity Technical Committee, we welcome you to our monthly webinar series and just restarting after a summer hiatus. So the committee composed of Ahmad Gassami, myself, Sean Maxwell with Ovintiv, Jens Lundstern, and Madi Haddad. We welcome you to our webinars. So today we're very pleased to have Paul Segall, professor with Stanford, presenting. He's going to be talking about the mechanics of induced earthquakes and reflections on the past and future directions. So Paul has a long history. We were chatting just before the webinar started. Paul claimed 40 years of induced seismicity history. So we're looking forward to a good webinar here. Before we pass it over to Paul, though, just a few housekeeping things, and I'll pass it over to Jens to talk about the schedule.
Thanks, Sean. Sorry for the technical issue there. We have a number of speakers lined up. These are the next two. This will be the first Friday of each month at a different time than we're meeting today, 1 hour earlier as usual, 10 a.m. Central Time. And so the first will be Mariana Rodriguez from ExxonMobil, and then we'll have Zijun Fang from Chevron on the 1st of November. So stay tuned for those.
Good morning, everyone. This is Mahdi Haddad from the Bureau of Economic Geology. A few housekeeping items are listed here. First of all, we have an invitation email list and send this webinar invite to that list. If any of your colleagues would like to be added to that list, please let us know. Please submit your questions during or after the talk in the chat function at the bottom of the Zoom meeting window. And send these questions to all of the organizers in order for us to be able to summarize the repetitive questions and have better use of time. And this specific webinar is being recorded after consultation with the presenter, and it will be uploaded in our YouTube channel after the webinar. And also subscribe to this YouTube channel in order to receive notifications for future uploads. I would like to highlight that please stay muted during the talk. We will have time after the formal part of the talk in order for you to have their conversation with the presenter or others in the informal part. And without further delay, let's invite Paul Segall to take over the stage. Paul.
Thank you, Madi. Let me share my screen here. Okay, how's that look?
That's good.
Okay, well, a few months ago, Jens had asked me to review the effects of pore elasticity in induced seismicity. And in part of looking at the literature that's gone on since I was really active in that, I did realize, as Sean said, that I have been working off and on induced seismicity since 1983 when the Coalinga earthquake occurred. And so I thought I would take an opportunity to look back at some of those results and see how I feel about them today. And so this is going to be in 3 parts, what is highlighted by these 3 figures here. At first, we're going to talk about production-induced seismicity that started with the Coalinga earthquake. And the conclusion there was that pore elastic effects are really the dominant contributor to inducing seismicity. So these are areas where you have significant pore pressure declines within the reservoir on either no or limited injection. And then about a decade ago, I got interested in thinking about, well, if pore elastic effects are dominant in production-induced seismicity, might they be playing a role also in injection-induced seismicity? And so that'll be the sort of middle part of the talk. And then the third part, which is more current and forward-looking, is really stimulated. All these have been stimulated by field observations, but this last part is stimulated by the the really incredible precise locations and the increased detections, which are emphasizing that when these faults light up with induced earthquakes, there are thousands and maybe tens of thousands of earthquakes. So that brings apart the thought that we have to think not just what are the processes that lead to the conditions for frictional sliding to start on faults, but what also is controlling when earthquakes stop. So let me get going here. Doesn't want to advance. Okay. So in 1983, there was this earthquake in Coalinga, which is in the western margin of the Coast Range west of the Central Valley. You can see there's some oil and gas fields here. And it was suggested to me by the late Jack Healy that perhaps this was an induced earthquake. That was not an obvious statement for two reasons, one of which is that there's a very thick sedimentary sequence between the reservoirs and the focal depth of the earthquake. We now think that the source depth was about 10 kilometers. And so there should have been thousands of feet of shale between the reservoirs and the earthquake, which you would think would hydraulically isolate the reservoir, the source region. And secondly, as you can see in this lower plot here, the pressures really decline. There was some gas injection starting in the 70s for gas storage, but really you have a net pore pressure decrease within the reservoir. So it was not an obvious call for this to be induced seismicity. So decided to look at that. And the first thing wanted to consider was the contributions from mass unloading. So you remove material, you're decreasing the load. So for a low angle normal fault, that would be reducing the, low angle reverse fault, which we have. You're reducing the normal stress, but compare that to the effects of pore elastic contraction. And so simple scaling arguments say that the pore elastic effect relative to the mass unloading is going to scale with the Skempton's coefficient times the shear modulus over rho gr, where r is distance. And the reason distance comes in is because pore elastic effects can be thought of as a superposition of centers of contraction, which are force couples, and so decay, the stresses decay is 1 power of distance faster. But when you look at that scaling, then at distances of, say, 1 kilometer, the pore elastic effects are about 1,000 times larger. And at 10 kilometers, it's about a factor of 100. So the conclusion is that pore elastic effects are going to dominate, except in very compliant materials. And the reason the scaling is so large is because basically shear modulus of rock is high. So just to emphasize what we're talking about with pore elastic effects and how that contrasts with just basic effective stress. So we have on a Mohr's circle where the horizontal axis here is effective normal stress. If you increase the pore pressure, you move the Mohr's circle to the left. But in pore elasticity, you're actually perturbing the total stress, not the effective stress. So in this little diagram here, it's showing both principal stress is increasing. But I want to point out that pore elastic stressing can perturb faults both towards and away from failure. It depends on the geometry between the fault and the sources, and it also depends on the background stress state. The third point I want to make is that pore elastic stresses do dominate in the far field. So this is a plot we made some time later, but this is log of stress and distance on this axis. The details don't matter, but the important point is that in the near field, what I call the direct effect, the friction coefficient times the pore pressure change, is significantly larger, but at some point the pore elastic effects are going to dominate. And the reason for that is when you change the pore pressure, you either increase or decrease pore pressure, you're either expanding or contracting the rock, and that generates an elastic stress, which is felt at distance. So pore elastic effects are always going to dominate in the far field. So I developed a model for Coalinga, and this shows for assuming it was the shallow angle fault plane, which was somewhat in debate at the time, that the pore elastic stresses did favor reverse faulting, but they were quite small, on the order of hundreds of megapascals. Now, I felt that this model, even though it was pretty crude, was plausible because it did seem to be consistent with the subsidence data. But now when I look back on that, I think that, you know, because this was a plane strain model, if anything, it overestimates the stress changes. So the conclusion was choline was probably not induced, although I don't think everybody agreed with that interpretation at the time. But while I was doing that work, I became aware of a number of cases where there did seem to be production-induced seismicity. One of these was in Alberta at the Strachan field. This is work of Bob Wettmiller, who showed that there were earthquakes that located beneath this gas field, and there was, as far as we know, no injection occurring. Well, somebody could correct me if that's wrong. But the earthquake started after some significant tens of megapascal drop in reservoir pressure. The earliest case I know of production-induced seismicity occurred in the Texas Gulf Coast, where in the Goose Creek field, there was subsidence due to production, and some normal fault scarps formed at the margin of the field there. And you see these gentlemen measuring the throw on the fault. These did generate some modest shallow earthquakes. There are cases of reverse faulting that were triggered. This was aseismic faulting in the Buena Vista Hills field. This is a little hard to see, but there's geodetic measurements showing contraction across this surface breaking reverse fault. And you see here in a bulldozer cut, the trace of the fault scarp. So it was offsetting this cut. This fault was creeping for, I think, decades, and the contraction caused buckling of pipelines. One of the more famous early cases of production-induced seismicity was in Wilmington, where the production led to this enormous subsidence, 10 meters of subsidence, which is quite significant because it flooded the city of Long Beach. But what got less attention were the horizontal strains. And you could see here, I don't know if you could read the scale, but this is in percent. So there's contraction of the center of the field of horizontal strains of about 1%, which from a crustal strain point of view is enormous. And this led again to buckling of railroad tracks and pipelines, and also generated a sequence of rather shallow earthquakes. These are about 0.5 kilometer depth. And we know the extent of those from sheared wells. These are very unusual earthquakes, are very shallow and very emergent waveforms, but we know their extent from these sheared wells. And I also want to point out that I was not the first to suggest porlastic deformation inducing these events at Wilmington. I found out later that Dan Kosloff had done that as part of his thesis work at Caltech. In any event, so we did publish this paper giving us sort of trying to put forward a unified perspective on production-induced seismicity based on porlasticity and looking at the stress perturbations that you generate from decreasing pore pressure or removing fluid from a reservoir. And the idea is that if you're in an extensional environment, like in the Gulf Coast, that those perturbing stresses, which are extensional at the margins of the field, could lead to normal faulting, but that if you're in a compressional environment, the compressive stresses, the horizontal compression that's generated above and below the reservoir could lead to faulting, including surface faulting, as we saw at Buena Vista Hills, Wilmington, and Alberta. So one of the cases that I thought at the time was we had the best data set for and looked into in more detail than others was the Lac field in southwestern France. This is work I did with Jean-Robert Grasso in the 90s. And this is a map on the left showing the outline of the anticlinal structure and the earthquakes. And on the right, you see the pressure history where the gas pressure drops many tens of megapascals. The first earthquake in the area, and there's a long historical record, so we know this is pretty well. The first earthquake was in 1969. Now, it did seem that porlastic effects were pretty well displayed by the surface subsidence, and I really like this data that we were able to put together that shows the surface subsidence being linear in the gas pressure drop. So that's what you'd expect for a linear porlastic theory. I want to point out here that the subsidence is much less. This is 6 centimeters, not the 10 meters that we saw in Wilmington. But of course, these are very stiff carbonates. I think they're Jurassic age carbonates. So the whole system is much stiffer. But we're able to model the subsidence reasonably well. And then to look at the porolastic stresses, we extended the axisymmetric thin reservoir model that Geertsma had developed and just extended that to compute stresses and showed that if you're in a compressive environment, so this is just east of the Pyrenees, that in this compressive environment, the porolastic stress changes were the area of increased porolastic stress is the area where the seismicity was occurring. So that was consistent. But again, these stress changes are modest, tenths of megapascal. So quakes in regions of positive Coulomb stress change. In looking back on this, there's some new work that's come out in the last few years. And Jean Robert has gone back and looked particularly at the effects of deep injection. This is a kind of a complicated slide where everything's normalized to the maximum value. The histogram is seismicity, the yellow curve is gas production, and the blue is the deep injection. And we knew deep injection was occurring back in the 90s when we worked on this, but we're convinced that it was really not a significant factor. Again, the first earthquakes occurred before any deep injection. So that's one point. But Jean Robert more recently pointed out that there does seem to be somewhat of a correlation between deep injection and the seismicity. And so they concluded that probably both effects are playing a role. Now, even more recently, this year, a new study came out evaluating the seismicity, relocating the seismicity over 50 years. And what they concluded is now that the seismicity is below the gas reservoir. The gas reservoir is shown here in red. There's a shallow oil reservoir up here, which doesn't appear to play any role in the induced seismicity. Back in the 90s, these depths were not very well constrained. And so depending on the velocity model and some assumptions that earthquakes would sometimes be above the reservoir and sometimes below the reservoir, it wasn't really particularly clear. But one thing this paper brought to my attention, which I actually had no idea about, is that gas production actually stopped in 2012 and deep injection continued. So this is some measure of seismic energy, and you see that the seismicity continued well after the production stop, and injection continued. And interestingly, if you look at the pressure measurements in this LA 102 well, this is the time when gas production stopped, and you see then this recovery in pressure. So this is interesting. You know, I just want to emphasize that the porolastic stresses, the stresses are going to scale with the pressure change, not the rate. So in any event, I think it leads to a more nuanced story now, and there's arguments, I think, in favor of both production and injection-induced seismicity. The evidence for production-induced seismicity is that the earthquakes, at least some earthquakes started before there was any deep injection. So we know, I think we know porolasticity is playing some role. The reservoir pressure continued to decline until 2012, and the surface deformation is consistent with a porolastic effect. The arguments in favor for injection are that the earthquakes continued after production stopped. Although remember, the porolastic stresses don't go away just because production stopped. They argue in this recent study that the largest events are located near the injection wells. There's this somewhat of a correlation between injection and seismicity. So I think, you know, my conclusion is the story is a little bit more nuanced than I understood back in the 90s. And but I do think with sufficient information about the reservoir models, we should be able to answer this question. Okay, at some point, attention turned to possible faulting within reservoirs. The emphasis I had in the past was stress changes either above and below or sort of at the margins of the reservoir. But at some point, people began speculating about, particularly at Ekofisk, is what I remember, that the earthquakes seemed to be located within the formation that was being produced. And one thing caught my attention were these stress measurements published by Larry Teufel in 1991, who showed, you can see these are for Ekofisk here, and this is for the McAllen field. Like it's pretty well established that as reservoir pressures decrease, the the least horizontal compressive stress also decreases. And that completely makes sense in a porolastic context. And we thought about this is Sean Fitzgerald and I looked at using an Eshelby model to look at stresses within the reservoir. So We actually looked at pressure decreases as well as temperature decreases because we were also interested in thermoelastic effects in places like the geysers. But if you decrease the pressure or cool the reservoir, it tends to shrink. So if you want to have it fit back within the elastic medium, within the elastic crust, you have to stretch it to get it back to fit. So that puts the reservoir into tension. So that, let me just say that that horizontal stress then scales with the pressure drop, the BO coefficient, which is bounded between 0 and 1, and a geometric factor, which depends on Poisson's ratio and the ellipticity of the reservoir. But that leads to sort of an interesting situation because you have a more tensile horizontal stress or decrease in compression, which would favor normal faulting, but you also have a pore pressure decrease, which inhibits faulting. And if you just look at that and ask what the critical BO coefficient would have to be, because the pressure change scales with the BO, the stress change scales with the BO coefficient, you find that there's a potentially unstable regime depending on the friction coefficient, the fault dip, and the BO coefficient, where you could actually get induced normal faulting within the reservoir. And my memory is that Teufel did do some experiments and estimated the BO coefficient for the chalks at Ekofisk and found them to be really quite high. Looking back at the literature, Mark Zobak and Zinke concluded that this was consistent with Ekofisk and in particular consistent with the evolution of seismicity from the crest to the flanks of the reservoir. I saw that Mark is on the Zoom today, so maybe he can comment if I misstated that. But anyway, if we try then to summarize the Coulomb stress changes in different environments around a reservoir, this is a little hard to see, but this is Coulomb stress on this, normalized Coulomb stress by the pressure drop on this axis as a function of fault dip here for a BO coefficient of 1 in a really kind of pancake-shaped reservoir. The effect that we were talking about just then is quite small, right? You can destabilize faults, but relative to the pressure drop, it's a rather modest effect. The stress changes above or below the reservoir are shown here. Let me back up there. So in this environment here, the stresses scale with the minor to major axis. And the reason for that is really simple. If this is an internal source of stress, if you integrate across a vertical plane, it has to sum to 0. So if you have large tensile stresses or effective tension induced within a very thin reservoir, then that has to balance a compressive stress spread out over a much larger volume. So that's a relatively modest effect here. Where you could get a very big effect is at the edge of the reservoir, right? So if you're outside, there's no pore pressure change. The continuity of stress says that at the tip of the reservoir there, the horizontal stress has to match within the reservoir. So that's probably why in places like Goose Creek, you've got significant faulting. And we did point out that this isn't restricted to this idealized case of pressure change and no pressure change, but that anywhere there's steep gradients in pore pressure, you could have a similar effect. Now, I don't think Groningen was on my radar back at this time, but I think other people have extended similar arguments to the Groningen case where you have sort of compartmentalized pore pressure decrease. So that was the production-induced seismicity. And as I said, about 10 years ago, I began to wonder whether if pore elastic effects are dominant in the production-induced environment, might they play a role in injection? And just to emphasize again, the classic Terzaghi effective stress, you're only changing the effective stress and the strength on the fault. But with pore elasticity, you're perturbing both the shear stress, the total normal stress, and the pore pressure. And the other thing that we wanted to look at was whether or not the space-time evolution of seismicity could be influenced by the time dependence of earthquake nucleation, or whether it was strictly just the fluid diffusion, the pore pressure diffusion, dominating the space-time evolution. So this is something I looked at with the student Xiaoyu Liu, where we took a very simplified model of a point source of injection in a homogeneous full space. We used the analytical theory of John Rudnicki. We assumed for simplicity that faults were everywhere located and uniformly oriented, and the hydraulic properties are uniform. Trying to make this as absolutely as simple as possible. And we use the Dietrich 94 seismicity rate theory to allow us to connect between stress changes and earthquake rate. So this is what kind of things that you get from these calculations, where this is distance versus time. You get the square root of time dependence for the pore pressure front. And the predicted seismicity rate looks a lot like that, right? So this is including both pore elastic effects and the earthquake nucleation effects. Details are going to change depending on the parameters, but I think the first order conclusion is that it's not going to be obvious whether pore elastic or rate effects are really significant from just looking at the average space-time evolution of the seismicity. That's not to say that pore elastic effects couldn't be important. The plot on the right here shows the relative difference between the uncoupled and fully coupled cases on a log scale, and it could make a difference, but the point is that it's still going to look like the square root of time dependence. At some point, the focus really shifted to triggering faulting on basement faults. And so Keiwan Chang looked at this where we have a simple model of injection into a permeable reservoir with faults within the basement, and contrasted the cases where faults are hydraulically connected to the injection layer and those where they're isolated. These panels are showing the direct effect, the friction coefficient times pore pressure change at different times. And the point is that, as you anticipate, when the faults are hydraulically connected, you can get significant effective stress changes on the order of megapascals. If the faults are isolated, by definition, no fluid pressure is getting within them. If you look at the pore elastic stresses in the well hydraulically connected case, they're not that significant. And they're still modest in the isolated fault case, but depending on the geometry, they could destabilize faulting, where these stress changes are on the order of several tenths of megapascal. So the takeaway is that, again, pore elastic stresses can be dominant for isolated faults that are not connected to the producing zones, but the effects are modest. So I went at Jens's request a while ago, I went and started looking in the literature to try to see if there are cases where there seemed to be good evidence for pore elastic effects. And a couple studies stood out. This is one by Thomas Goebel and others, where they looked at the Fairview, Oklahoma earthquakes. And these earthquakes are rather far from the high volume injectors. And they concluded that even if you put in highly conductive pathways, the pressure changes on these clusters of earthquakes were less than a few hundredths of a megapascal. They computed pore elastic stress changes and found that they were in fact larger in that case. So here, these are histograms assuming different diffusivities, hydraulic diffusivities that, let's see, these are on the order of hundreds of, I can see better here, less than 5/100ths of a megapascal change, but in the pore elastic stress are sort of an order of magnitude bigger. So this is, again, in this case where the argument is that these are in the far field, so the pore elastic effects are dominant. Another case that seemed interesting, I think, and somewhat convincing is from some hydraulic fracturing in the Crooked Lake area in Alberta. This is by Dangler and Harrington, where they computed pore pressure changes on the fault that were very modest because they're injecting into shale, but found pore elastic stresses on the order of tenths of megapascals. Now they concluded, they have two arguments to suggest that pore elastic effects are dominant. One is just looking at how the fraction of events that fall within a potentially destabilized region vary with permeability. We think the shale permeability ought to be less than 10 to the minus 16, which would put, so if you look at the left axis here, only about 60%. So roughly 50% of the faults earthquakes would fall within a predicted zone to be destabilized. If you increase the permeability, of course, you extend the area where the pore pressure disturbance reaches, you extend the volume. And so you could eventually encompass 100% of the earthquakes, but then you get pore pressure changes that are less than a few hundredths of a megapascal. So that was one argument. The other argument they put forward is that the location of the events did seem to correlate with areas of positive induced shear stress, which would indicate a poroelastic effect. I was always looking for a smoking gun. And one smoking gun potentially would be that something that Xiaoyu discovered. And, I scoured the internet for a picture of Xiaoyu and I couldn't find one. Then I realized I'd been invited to her wedding. So I had this picture. And this is not the way she dressed as a grad student, just FYI. But what Xiaoyu discovered, I think quite accidentally, was that if you inject for some constant interval, inject at a constant rate for some interval, and then suddenly stop injecting, and this is an important if you're in an environment where the poroelastic stresses are inhibiting faulting, which was the case she was looking at, when you stop injection, because that's in the far field, those stresses relax at a time when the pore pressures are still increasing. So you're effectively unclamping the fall at a time when the pore pressure is still going up. And that could lead to this bump up in the Coulomb stress. So I looked mightily to try to find examples of this and felt that I was unsuccessful. But recently a paper came out by Coralla and others in EPSL where they say they have found exactly that effect. And this is in the Blue Mountain geothermal field, where during shut-ins, there seems to be bursts of seismicity. And that occurred in 2017, 2018, but apparently not in 2019 for reasons that I do not understand. But they modeled the poroelastic effects and found exactly as Xiaoyu did, that the effect of poroelastic stressing was to inhibit faulting. So when the shut-in occurred, you got a bump up in Coulomb stress, as you see here. These are, I guess, different models for different diffusivity. The shut-in is during this blue period. You see this increase in seismicity rate, which is in the dots. Now, I have talked to the authors a bit about this. They believe this is not a noise artifact. Now, I saw one other case where I got all excited and then eventually concluded there really was an artifact of the effect that once you stop injecting, the noise level went down and we're able to detect smaller earthquakes. They've looked at that and have concluded that's not what's going on. They also feel it's not due to repressurization near the production wells, because you have both injection and production going on. So I think this is really, really quite interesting and bears further work. My own bias is I'd like to see a better reservoir model, because the model they used, I think, is quite simple, and perhaps better earthquake locations before we're convinced this is really the smoking gun. I did want to turn to this just very briefly for one slide, this question of rupture extent. This is obviously something that a lot of people have looked at, whether or not the perturbed volume controls the extent and therefore the magnitude of the earthquake. There have been a number of approaches. I've listed some here, and an argument has made, I think, prominently by Nicholas van der Elst, that really the sizes of induced earthquakes are no different, follow the same statistical distributions as tectonic earthquakes. But Jeremy Moore did address this in a way that I thought was interesting, and that is to use Eric Dunham's dynamic rupture modeling code, because you'd think that cases that would be most prone to having the volume of perturbed pore pressure controlling rupture extent would be in areas where the tectonic stresses are low. So earthquakes have a hard time propagating on their own, and the perturbation is rather large. So Jeremy looked at a number of cases. I'm only going to show one here where there was, because of a high permeability region, the pore pressure was high within this shaded region, which maps on to this here. And what Eric's code allows is you have to artificially nucleate an earthquake, but then it could propagate on a rough fault. And we'll talk more about rough faults later, but the reason this is important is we wanted to include some other measure of heterogeneity, so that once a rupture is started, there are other effects that can stop it other than just the extent of the pore pressure disturbance. So in this one particular earthquake simulation here, you see it started an earthquake here. As it propagated to the right, it did seem to stop somewhat near the high pressure boundary, but at the other end, it propagated farther. So we found that only in rather limited cases and that's cases as you anticipate, with low background stress and rather large magnitude perturbations, did the pore pressure trap the ruptures. The issue with this is because this code only models dynamic rupture, we had to somewhat artificially set the initial conditions. So, right, you're not going to get a very large pore pressure perturbation without having any earthquakes at all. So I think this is an area where more work needs to be done, where we include cycle models to naturally spin up these sequences. Okay, so now to summarize the pore-elastic effects, I think it's just important to remember they're present. They're invariably there. They're modest in magnitude, but they will tend to be dominant in the far field, and they'll also tend to dominate if you have faults that are hydraulically isolated from the areas that are being perturbed. I think they're plausible field cases and maybe now a smoking gun, but I think a little more work needs to be done. And one thing that hasn't really gotten any attention that I think is worth thinking about is that we could test these models with in situ strain data. So there are strain meters, borehole strain meters, the kind that were deployed for the Plate Boundary Observatory, that would allow us to measure strain perturbations over time. And if we combine that with pore pressure monitoring, I think we'd allow us to really calibrate these models and test their effect in situ. Okay, so that kind of brings me up to the present. And this other set of observations, which one day in one of our Stanford Center for Induced and Triggered Seismicity seminars suddenly hit me that with all these improved earthquake detection and location methods, we're getting these really remarkable views of what these fault structures look like. And what we see is, of course, that these faults are hosting hundreds and thousands of events. And that means that earthquakes are continually starting and stopping. This is no different than tectonic earthquakes. Another observation I thought was really interesting from Young-Soo Park and colleagues is that in some cases in Oklahoma, these fault structures light up with microseismicity and then subsequently experience full fault ruptures and generating greater than magnitude 4 events. So just the fact that these earthquakes experience a lot of seismicity doesn't mean they've relaxed all the stress and they're capable of generating further events. So I would argue that this really means that we need to worry about heterogeneity. We could argue about nonlinear dynamics and how much of this can be explained, but I think that it does require heterogeneity, and we have lots of sources of heterogeneity to think about, right? There's heterogeneity in material properties. There's also heterogeneity in stress due to previous ruptures, whether they're seismic or aseismic. But one thing that's gaining more attention in the last few years is fault roughness, and that's because we know that faults in the field are rough. They're rough on all scales. They have self-affine power law distributions in terms of roughness. And we also know that there's other evidence that fault roughness probably plays a role in earthquakes, and that's from work of Eric Dunham looking at dynamic rupture simulations on rough faults, where he has shown that they produce high-frequency radiation, so they have acceleration spectra that look a lot more like natural earthquakes than ruptures on flat faults. So this is work that was started by Camila Catania when she was a postdoc and has continued now that she's at MIT, and where these are two-dimensional plane strain simulations where the fault is fractally rough, but is everywhere velocity weakening, and the frictional properties are homogeneous. So that means in principle, if the normal stress is high enough, any place on the fault can nucleate an earthquake, and these faults are loaded by constant far-field stressing rate. So this is a kind of results that she found, and I want to explain this plot because you're going to see a number of them in the forthcoming slides. So this is the spatial coordinate along the fault on this axis, and you see the very heterogeneous distribution of normal stress. On the time axis here is, in this case, is log time to the main shock. We'll call it a system spanning rupture, a rupture that breaks the whole fault for simplicity. I'm just going to call the main shock. The color scale here is the slip speed, the log of the slip speed. So these blue areas are locked effectively. The pale green and yellow are creeping, and the red are dynamic. So what Camila showed was that this very simple setup leads to cascading sequences of foreshocks and accelerating creep, where the creep is promoting foreshocks and the foreshocks are accelerating the creep. So it's a fully interactive process. And she showed very nicely, both empirically from the simulations and also theoretically, that both the average slip velocity and the seismicity rate increases as 1 over time to failure. So this is log time to the main shock. And this is what has been observed in stacked foreshock catalogs. So it was consistent. So what we've been doing, and she and her postdoc, Xin Kui at MIT, have also been looking at similar things. What we have been doing is trying to make parameter setup that's consistent with Oklahoma, where the far-field stressing rate is quite low, so that we get main shocks every half a millennium or so. The nominal effective stress are consistent with what you'd expect at, say, 4 kilometers depth. And we pressurize the system. We add pore pressure at a rate of about 1 megapascal per decade. And we do that at a constant rate for simplicity, and also for simplicity, make that spatially uniform. So that would be the case if the injectors are quite far from the fault. This is some work that Leonardo Aguiar is doing as a second project. This is a similar kind of plot. The difference being here is the onset in the pressurization is here, and these don't show up terribly well, but there are a series of foreshocks that occur in the decades after injection starts. And then as you get closer, sort of in the several days before the main shock, there's a cascade of foreshocks that ultimately leads to the main shock. Now, one of the things that's important that Camila has emphasized, and that is that the creep transfer of stress onto the locked asperities is a very dominant effect. So for this figure, I've just plotted time axis here as the solver time set. So it sort of pulls this apart a little bit. And you see, for example, there's over here, there's a series of foreshocks. So injection started about just before this first foreshock. And you see the creep rate, you get a lot more yellow. So the creep rate accelerates due to injection. And then there's a sort of cascade of foreshocks. And if we look at the contribution of stress on the asperity that breaks for this third foreshock here, again, this is in solver time steps. So the pressurization, which is a constant rate, is weakening the fault. That's actually linear in time, but you see its amplitude there. Oops, I didn't want to go ahead. The tectonic stressing rate is very modest. What's shown in red here is the elastic stress transfer onto the asperity that eventually fails. And you can see the stress transfer due to the first and second foreshocks, and then this very large accelerating stress, which is due to the creep penetration of these creeping zones, sort of act like cracks that propagate in and erode this high normal stress asperity. So you see it in terms of velocity here, and I think more usefully in terms of the stress concentration. This is like a crack tip propagating into the asperity until it ultimately pops and generates the foreshock. So one of the things that we're interested in is sort of understanding in the context of these models how the critical pore pressure, that is the pore pressure change required to nucleate both the first foreshock and the main shock, and how that varies with time through the unperturbed earthquake cycle. I guess I should have said that we run through several cycles that have intervals of about 500 years duration, and then introduce the pore pressurization at different times. So say 50% of the way through the cycle, all the way up to 95% of the way through the cycle. Question is, it'd be more fun if we were in person, what you would predict this relationship to look like. And I think you'd expect that it would decrease, right? So that if you're early in the cycle, the shear stresses, the tectonic stresses are low, it's going to take a larger perturbation to nucleate an earthquake. And as you get closer and closer to the time when the earthquake would have occurred anyway, it's going to require a smaller perturbation. You might also, that's going to be true for both the first event and the main shock, and you might expect that the sort of distance between those two curves would narrow. And that is in fact the case with a lot of variability. So the red shows the pressure perturbation necessary to nucleate the main shock. And we have 10 realizations at each point here. So you see the distribution. This shows a 1 sigma error bar. I will emphasize these are not really normally distributed. And in particular, the case for the pressure change to the first event is not at all normally distributed. But it does sort of follow intuition that takes less of a perturbation. And you can see where it stacks up. There's a lot more here. So yes, the time to, you could think about pressure and time is related because it's a constant rate. It does decrease, let me go back here, does decrease as you're later in the cycle. But I think it's interesting to look, because this is lumping all the 10 cases together, to look next at the pressure increment between the first foreshock and the main shock. And here you see just how much scatter there is. I mean, there is a downward trend. If you're late in the cycle, the critical pressure difference between the first event and the main shock is in fact smaller, but there's such a wide variety that in some ways it's I think a bit alarming. So for example, even halfway through the cycle, the pressure difference between the first event and the main shock is quite small. And that would indicate relatively little warning, right? The pressure necessary to generate the main shock is almost there by the time you got the first event in this case. In contrast, you sort of get the opposite extreme where, and I should have said that the surprise is that could occur even when the tectonic stresses were quite low. In contrast, you have other cases where the pressure difference between the first event and the main shock is rather large, even though you're modestly far through the cycle. So this could indicate you have cases where there could be an extended foreshock sequence and yet still a main shock yet to come. And perhaps that's some of the cases that in the Park et al. Study where the main shock has not yet occurred. So this, again, just emphasizing how much variability there is. And that led me to wonder, what about seismicity rate? Not just the pressure to a particular event, but the rate of earthquakes would occur. And I don't know about you, but my intuition was if we're up at this end here, where we're getting close to the main shock, just stresses are high, that you'd think that injection would really kick off, make the seismicity rate become very high. Whereas if you're much earlier in the cycle, you'd get a more modest rate. So Cheng Mai, who's a postdoc, and I looked at this, and this plots effective seismicity rate. This is 1 over the interevent time, which is also what Camilla used. And for these different situations, 90% of the way, 80%, so forth, 50% of the way through the cycle. So let me just walk you through this. The horizontal axis here is time to injection. So 0 is injection. So the 90% case is the only one that has significant foreshocks before injection. And this curve here is this 1 over time to failure, where I've taken the mean time to failure for the 90% case and just project that forward. So this is what you'd expect the seismicity rate to follow. And you can see after injection, all the red points are, somewhat above that. So the seismicity rate is higher than you would have anticipated. And of course, that makes perfect sense, right? You're forcing the system at a more rapid rate. but it's not that much higher. Of course, this is a log scale. But to me, what's even more surprising, if you look at the other cases, say the pink, blue, green, and black, if you look at the sort of, and you tend to focus on the smaller inter event times, because the smaller rates, the larger inter event times, because you're going to get these sort of triggered events, which give you very short intervals. And anyway, the bottom line is, when I look at this, I have a hard time seeing a significant difference between these different cases. And that would suggest that seismicity rate in these kinds of models is not terribly sensitive to the background stress state, which if I should say that's a rather new result. If that holds up, I think it does have implications for forecasting. So in conclusion, we see this profound interplay between creep and foreshocks. That pressurization not only decreases the effective stress acting on asperities, it accelerates the creep in kind of an exponential way. And that accelerated creep stresses the lock asperities. We see the threshold pressure change decrease with stage in the seismic cycle, as one would expect, but the roughness introduces very significant variability. In some cases, this compresses the foreshock sequence, so you would expect relatively little warning time between the first foreshock and the main shock. And in other cases, leads to what you might think of as anomalously long foreshock sequences, so that one couldn't conclude that there's not a main shock lurking in the future. And again, pretty preliminary results, but that does appear that seismicity rate may not correlate terribly well with background stress, which I think does have real implications. So I think that's it. And I realized I forgot the acknowledgements on my first slide, so I'm going to try to go back. But before I do that, I did want to just acknowledge the late Jack Healy, who's shown here on the left with Barry Raleigh. When I was working at USGS as a young scientist, a freshly minted PhD, I appreciated, first of all, Jack's stimulating hypothesis that Coalinga was an induced earthquake, and Barry was the office chief, and my branch chief at the time was Mark Zobak, who was on the call and worked with over the years. And they all gave me the freedom just to explore these problems, and for that I'm very grateful. And if you all just permit me, because I skipped over the acknowledgements on my first slide, I did want to thank, I think I touched on everybody, but I did want to thank Leonardo, Chang, Camila and her postdoc Shin at MIT, and Eric, and also funding from USGS and SCITS. And so let me stop there and thank you.
Great. Well, thanks for the presentation, Paul. Lots of really intriguing examples and concepts there. So I guess we have a few minutes here for what we view as kind of the formal part of the Q&A, and then we can maybe wrap up. And if you're willing, Paul, we can maybe continue the conversation more informally with people. There's a few questions in the chat window, one of which, or two of which rather, Ryan Schultz and Zhijing Feng both point to sequences during shut-in. And I think from my perspective, the Duvernay Shale is kind of an interesting example where there's, I think, a number of scenarios where after hydraulic fracturing during shut-in or flowback, there's increased sequences of seismicity. And I'm just curious, I guess, Paul, have you looked at any of those? And do you think the flowback, so hydraulic fracture and then shut in and then start to actually flow the system back, would that still be analogous to your kind of smoking gun example where you think poroelastic would be a significant contributor?
Sean, I don't think I can speculate without knowing a little bit more about it. But people are able to share some of that data, I'd love to have a look at it. But I don't think without knowing more about the setup, I could speculate. I would just want to emphasize this only happens in cases where the poor elastic effect is inhibiting, right? If poor elasticity is favoring faulting, then you're not going to see this effect, or you would not predict to see this effect. And it also has to be where the sources are in the far field, where so that the poor elastic, so when it's inhibiting, you relax that inhibition before the pore pressure change hits the fault. So it's kind of a nice test, and it's very specific, but it may be hard to find.
So kind of building on that, I guess Ryan asked a second question, which I think is a very good one. There's a lot of discussion about poor elastic effects, and as you pointed out very clearly, there could be very nuanced differences from just the direct pressure effect to poor elastic. And could you maybe talk a little bit more about potential observations, maybe like the shut-in observation that might be diagnostic to separate the two mechanisms?
Well, as I said, if I think about it, now this is non-trivial to do, but I think strain meters are the way to go. And because you're really directly measuring the thing you care about. Alternatively, and this would be something that actually Mark and I had years ago talked about doing at Locke, at the reservoir scale, if there were cases where there had been hydraulic fracturing, so to measure at least, or even what do they call them, the mini fracs? Mark's the expert on this, where you're measuring the least principal stress. If you go back over time, poor elastic theory would predict those stresses would change. And if you could go back, reoccupy those, and just repressurize those fracs, you could test whether you're actually seeing the stress changes that are predicted. And that would be a really nice way of trying to test some of these calculations.
All right, excellent. But maybe what we can do is take the opportunity to formally wrap up the webinar, and then we can continue the conversation again. Paul, if you're able to stick around, to be great. So on behalf of ARMA and the Induced Seismicity Committee, thank you very much, Paul, for the presentation. Again, great overview, lots of very interesting insights. I should just bring up my schedule here and remind myself of so the next webinar will be October 4th, back at the normal time. Mariana Rodriguez from ExxonMobil is going to be presenting. She had a ERTEC paper at the beginning of the summer, so she's going to represent that, and I think include some additional examples. So be a good webinar, so watch out for the invitation coming from Mahdi. Thank you everyone for attending. So Paul, I don't think I gave the combination of questions there maybe as much justice, so maybe we can typically what we do in the informal part is invite people to unmute, and I see Mark's unmuted and on, so he may have comments from multiple colleagues from you. Go ahead, Mark.
Oh, it's not pressing. Well, thank you, Paul. That was a great overview of a lot of material. The one the one thing I'd point out about the poor elastic effect in Oklahoma is that, in the global study, they're looking at sort of a radial flow system, and the fact that at distance, the poor elastic effect is bigger than the pressure change, but it's not a radial flow system. The Arbuckle is like, multiple Darcy permeability, and the pressure spreads out very widely, and then downward, into the critically stressed faults in the basement. So that was one example in which I was just never convinced that poor elasticity. It's obviously there, right, and it's obviously having an effect, but I don't think it's the driving force simply because a well is further from the earthquake than one would think would be appropriate for radial flow. It's really not a radial flow system. It's a linear flow system from the highly permeable Arbuckle down, down into the basement rock. But I thought it was a great presentation. So thanks for
Yeah, well, you notice I said we're still waiting for a smoking gun. I also noted, as I understand it, their stress calculations were two-dimensional, which would overestimate the pore elastic stresses. So even accepting the pressure distribution, I think they may be overcalculating the stresses. So, and there's more to be done, I think, in a lot of these cases.
Agreed.
So I see Ryan's there, and Ryan had a couple questions. So I tried to ask him, Ryan, but
Yeah, no worries. You did very well. I just wanted to poke a little bit more about one of them. So your ideas about the shut-in poroelastic effect is very cool. And you gave like a basic situation where that would happen, where you're saying it has to be inhibiting the poroelastic effect initially, and then once you stop the shut-in, then that releases that, and you can get that quick burst of seismicity potentially. Is there a situation, or have you thought of a situation very analogous to that, where when you start flow back, you would start to get seismicity, or would that be the exact same thing?
Intuitively, it feels similar, but maybe bigger in amplitude. If you're actually dropping the pressure, then it feels similar, but I haven't tried to put numbers on it. Excuse me.
No, that's fine. I'm just asking for speculation, I guess, or what your intuition might be for that.
Yeah, in the tighter the formations, the more spatial variability is. Having accurate locations and knowing where you are relative to being accurately able to predict what the stresses and pore pressure changes becomes important. So
maybe if they're both
locations, but
if they're both the same, potentially these two effects, then could you use the difference in seismicity rate or something like that between what happens at shut-in versus flow back to calibrate something within the model itself? Or, and I know I'm kind of going far out on a limb here now, but
yeah, I think so. But I'd love to establish that it's a real effect first.
yeah, sure, fair.
I didn't say this, but there was a workshop many of you were all at in Banff, where there was a talk given where it was reported at Decatur there was an increase in seismicity on shut-in, and I got very excited. I thought, well, this is the example we've been looking for. But then Bettina Gutz-Holloman and I sort of dug into the data and realized that it was a bit pathological, because the one downhole instrument, this is the first phase of Decatur, the one downhole instrument was in the injection well, the same well. So when or right nearby, somehow very close. So when they shut the pumps off, the noise level went down, they start detecting more earthquakes. And Bettina wasn't 100% convinced, but I would say at the 95% confidence level, we decided it was just an artifact. So I think one has to be really careful about that. These authors that I mentioned did look at that. I had email exchange with Thomas about it, and they're convinced it's not a noise effect, but one has to be very careful about that. I think you get fooled.
Yeah, that's fair. But well, thanks for entertaining my questions.
So I think the next question in the chat was from Zhejiang Feng, who I see is here, and I think you have a couple, Zhejiang. Do you want to go ahead and unmute and ask them?
I'm not hearing you.
Yeah, your audio is not coming through. Still can't hear you. Oh, maybe now. Try now.
How about this?
Yeah, that's working now.
Okay. So hi, Paul.
Hi, Zhijian. Nice to see
Thank
you.
Okay. So a couple. So one comment first. So actually, there's cases we see when the in hydraulic fracturing when pumping is stopped, just immediately after pumping stopping, there's a pop up of induced seismicity. So that's to me that is very analogous to what you describe because when you stop pumping, then the hydraulic fracture closes. So it really affects the surrounding stresses. So I guess some of the fractures that was inhibited, and then they also see some uh, additional leak of pressure coming in later. Yeah, so that could be one
Yeah,
explanation.
I think, I don't, if you could share some data, I'd love to see it. That'd be great. I don't know if you're
Yeah,
allowed.
yeah. I mean, that's always something I want I want to do, but it's really hard. Okay, and also we see that in CO2 injection too. Yeah. Uh, one question I would like to get your insights is that nowadays there are two practical methods that essentially can help us relate induced seismicity to the operations. One is typically we use the using the Dietrich formulation that you first used 10 years ago, and there's a whole bunch of papers coming up after that, and we develop that workflow, and probably after 2 months you will see how we apply it to Delaware Basin induced seismicity. But one constant question I got is that how would we do for any field that has no induced seismicity at all? Is there any methods, even with big uncertainties, that we can use? So I scratched my head like a long time, and I thought maybe we can use Jim's IQ thing to do a uh, parameter space screening and get some responses. And we build up the model, and we try to simulate the earthquake sequences, and which we try to match to some known induced seismicity sequences before we can build trust internally. But a lot of times, what we have seen is that because the induced seismicity typically are small events, and the fault plane is big, so it's really hard to restrict those events because sometimes they nuclearly they grow out. So then I introduce roughness to it, but still trying to keep them at place. I really have to go really small roughness, and in exchange, that really burdens the computation. So it's like a kind of a dead end. So I would like to hear your opinion, like uh, for anything that we don't have induced seismicity. Any insights on that?
I'm not sure I got what the one question was. I mean, is the question, could you just sort of synthesize
It's
the,
like a couple. It's like a couple of questions. So one is like if there's no field, it's a field, and you can have some hypothetical operations, and can you at least guess or give some scenarios of possible future induced seismicity? And a question following that is that I try to use ISQ thing, but I had a problem in restricting small events grow into big ones.
So you're saying in a prospective sense, beforehand, can you make any assessments? Well, I mean, the first order thing, I think what people do is just assess what is known about the in situ stress state, what the predicted perturbations are. Mark and Jens, I'm forgetting the name of the code that you can evaluate.
FSP, Paul.
FSP, thank you. FSP code will give you, the sort of first order assessment about whether, given what's known and given what the predicted perturbations are, will give you the first order prediction of whether you'd see seismicity. One of the goals of the work that we've undertaken is trying to use the induced seismicity to sort of calibrate what the amplitude of the heterogeneity is. I mean, I think we all agree there's some heterogeneity. Right? So what the average stress is, pick a number. Right? What is the variance about that? What are its spatial characteristics? If it's self-affine, that's okay. But what is the amplitude? And one of the goals is to use these observations to try to calibrate that so we could directly address the second part of your question. Both in injection-induced seismicity, but also just in tectonic events. I think we need to know what the variability in the natural stress is when we're trying to model these events. So I don't have an answer yet, but that's definitely one of the goals.
Okay. Thank you.
Great. So moving on, I see Mirko on. Mirko had a question about water hammers.
Yeah, since I have all the experts here in front of me, Paul, you showed that change in the poroelastic effect during the shut-in and restart. I've heard many operators say is that especially during maintenance of saltwater disposal wells, they try not to change the volumes too dramatically to prevent water hammer effect because they have seen burst in seismicity associated with that. The water hammer effect is the change in momentum in a fluid system, moves, stops, and that causes a very big force. So is what you're showing the same or is it completely different?
So tell me what is actually being done during this maintenance period?
So the water hammer effect is, in these old tubes, when you turn the water on or off.
Yeah. No, I know what water hammer is.
Okay,
what are the operators actually doing?
So what I'm told is when an operator in a saltwater disposal well, they don't want to change the volume from, say, 100% to 0 in a very short time frame because that's going to create a water hammer effect. So they do it a bit more gradually around this part. And that's both during shut-in and the restart. So this change in poroelastic effects, in your case, is this related to the time frame over which the injection starts or stops, or is it a completely different effect?
Maybe just to add to it, I think the way I understand a conventional water hammer would be just a pressure transient from that sudden pressure change propagating the system as a triggering mechanism.
So you're saying when you say volume, you mean flux? They
Volume rate. Yeah, rate. Sorry.
They don't want to change the rate rapidly. So yeah, I mean, certainly a pressure transient could have an effect, and I can imagine cases where you could get transient stresses that could get pretty high, but it reminds me of an old story. How long do we have? When I took fluid mechanics from Channing Robertson at Stanford, he told a story where he put in his own sprinkler system and to water his lawn. And he thought he was a clever guy and he put some automated valves on. And unbeknownst to him, these were very fast acting valves. So when he turned it on, everything worked fine. He was very happy. He shut it off. He got a water hammer and just blew the PVC piping out of the ground. It's just, you got an eruption where the whole sprinkler system just erupted out of the ground. It's such a large pressure transient.
Well, at least you didn't induce an earthquake, Paul, so
Yeah.
it's maybe a good thing. So I guess moving on, there's a number of congratulatory comments, and Peter, I'm gonna butcher his last name, Eichhobel. I don't see his on, but I see Ernie's on. Ernie has a question, and he's also looking very cool, and he must be on a beach somewhere. Ernie, do you want to ask your?
Does someone capture the chat? Because I don't know if I can do that. It'd be great if someone captures the chat questions so I can look at them later.
Yeah. Well,
Yep.
okay. Hi, Paul. Thank you.
Ernie.
That's great talk. In the geothermals, you're well aware of, and they do a lot of induced seismicity issues in geothermal. You and Mark are both aware of this. But a big deal now, of course, is getting in an appropriate traffic light system. You know, how do we know when to stop? How do we know when to start? Things like that. Uh, I see the work you've been doing would have a lot of application to coming up and improve traffic light systems. What is needed is a real-time, accurate traffic light system, of course. Or you always go back and say, well, we should have stopped it there, we should have stopped it here, you know. But introducing some of the thoughts that you have, it would be great. Have you or Mark ever thought about improved traffic light systems with not only in oil gas applications and in hydrofracture applications, but in geothermal applications?
Well, I think is Ryan still on? Because he would be
Yeah,
the,
I know Ryan. You know,
yeah,
and
done
part of
really-
geothermal, they're trying to do that.
Yeah.
And they have come up with great ones, you know. But how about yourself in terms of?
No, that hasn't been I mean, I'm having a hard enough time keeping up as it is without adding new tasks on my list. But no, that hasn't been one of the priorities for us at this point.
Yeah. Because the geothermal people, if they're going to meet their goals in terms of production of alternative energy, which is quite lofty goals, they're going to have to go closer to populations. And if you don't have good mitigation practices, you can't do that. And so it's really important to I've had a few bad experiences in the past and had a lot of experience up at the geysers. There's a lot of non-engineering mitigation techniques as well as engineering types of everything from paying off the community to insurance, you know. But I'm just wondering. But I can see a lot of applications.
Well, I will say one thing, and that is that Eric and I are going to be working with Fervo on one of the cases where they are getting induced seismicity, and they're going to be sharing the downhole data as well as the seismicity. And we're going to try to look at that in detail. So I think we are moving in that direction, not in the traffic light sense, but in trying to really see how far we can push these models in cases where we have really good data.
Yeah, they have really good data. I know what you're talking about out at the Cape near Forge.
Yeah, exactly.
So, yeah, we're collecting some of the data. So,
Ernie, I would simply add that, you know, traffic light systems work great in some contexts and are probably the inappropriate tool in others.
yeah.
Geothermal, you've seen cases where people, you know, they've got 10 years of work in a given project, and if they stop, they've got nothing to show for it, and they blow past, right, the original traffic light, and then bad things happen, and eventually they do stop. So I think the appropriate tools have to be, you know, they're contextual, and it might need some other tools in addition to traffic lights.
Yeah, that's what they do out with the guys is they have other tools, not engineering tools. All right, thank you.
So that sparked another question from Veronica Montoya. Veronica, I don't know if you want to unmute and ask your question. It may be more of a comment.
Yeah, it's more of a comment than a question, right? But yeah, I was just kind of piggybacking off the previous question about, traffic light system for geothermal applications. I think that, with CCS applications, and in particular, I live in Midland, so I'm impacted by induced seismicity. And I get worried about the Railroad Commission is seeking primacy for Texas when they haven't done a great job with saltwater disposal, regulatory issues. And so, yeah, it's more, I guess, a comment than a question, but just curious to see what other people think about the CCUS applications.
I don't know if anybody has. Oops. I think it is an important topic, and actually one of the upcoming webinars we're gonna try to target to have a panel to talk about the issue with a combination of industry and academics. We haven't completely fleshed it out, but we are.
Peter Hennings and I are writing a review paper on the implications of the earthquakes caused by water injection for large-scale CCS. And hopefully in a few weeks or a month, we can have something to circulate, and that may be of interest. But this is Paul's seminar, and that's
I mean, this is just time for chatting, so that's fine. One of the comments did mention something about temperature changes, and that's something that we did look at in the context of the geysers. Back when Tony Mossop was my student, and we looked at it at the sort of in terms of the contribution to the net subsidence and stress change at the sort of reservoir scale. And Tony also did some work that was really never published on at the scale of a single injector, and that's unfortunate. But I think thermal effects can be significant and sort of underappreciated.
Does anybody have any other questions for Paul? Well, again, thanks for doing the webinar, Paul. Really appreciate it, and generated a lot of interest, as you see.
Yeah, thank you all.
Thanks, Paul.
Yeah, it's good to see everyone.
Thanks, Paul.
Yeah, take care.
Thank you so much, Paul.